Hello all, I'm sorry it took so long to prepare the next video, but I ran into trouble with my old iPad, which resulted in me buying a new one and so on. So hopefully now everything will be okay. We were left at topic 11, and you can see how the handwriting is slightly different due to the new iPad. So topic 11b, which is going to discuss space, okay? And let me adjust this pen. It looks a little bit weird. Let's do ball pen, I guess. Okay. The thickness. Okay, this looks better, I think. So let's move on. Now, in topic 11a, we talked about gravity, we talked about satellites and so on. But to get to the gist of this topic, we have to talk about stars and space in general. So let's start by saying that everything we know about stars this is too thick. Let's see, let's make it thinner. Okay, everything we know about stars and the universe in general stems or comes from electromagnetic radiation emitted. In the case of stars, light is emitted or reflected. This is for the case of planets, right? Planets generally don't have their own light. Okay, you have lightning and this kind of phenomena, but in general, some star in a solar system sheds light on a planet, and then the planet reflects that light and we are able to see it. Of course, there are other ways to see it, such as, for example, I had colleagues back at the University of Notre Dame when I was a graduate student that detected exoplanets by looking at stars, and they were waiting for the moment when a planet will pass in front of that star. Therefore, you will see something like a dip in the emission of the light from that star, and that will tell you that a planet passed in front of the star, therefore there is an exoplanet, and so on and so forth. So that's a little bit crazy, but in general, I want to stress how everything we know about stars comes from light, really dim light sometimes, because it comes from literally millions of light years away from stars that are like millions of light years away from us. So we have to collect that light, and that makes us able to infer properties and other things related to stars and planets. So sorry for digressing. So radiation emitted or reflected, I wrote there, by stars, or in general, celestial objects. Celestial is with a C, I think. So celestial objects. Planets, pulsars also emit light. Neutron stars, etc. Okay. Now that's one way. It's not the only way. I mean there are a few exceptions, such as particles. So we also receive particles such as the solar wind, the solar wind consists of usually protons, helium-3, nuclei, etc. So we also receive particles, cosmic rays. Cosmic rays are ultra fast particles from supernovae. We're gonna talk about all these things, guys, okay? And also, and lately, one new, very, very new, literally 10 years old, maybe a little bit more, I think it was 2014, when the thing that I'm gonna just mention was discovered. So, and lately, gravitational waves. Sorry, I ran out of space there. Gravitational waves. These are mechanical waves in the sense that they make a mass, oscillate them. So just like electromagnetic waves are felt by electrons and protons and that kind of thing, gravitational waves are felt by masses, like objects with mass, okay? So, and these gravitational waves are produced when two neutron stars merge, or two black holes merge, or other violent in general phenomena like that, okay? So, at the A-level physics, we will focus mostly on electromagnetic radiation, which is the most common thing we receive from space, okay? Because gravitational waves are really rare. Cosmic rays are actually not rare. They are observed all the time. Same goes for solar wind, but we're not going to talk about that. We'll mostly talk about electromagnetic waves and stars and stuff like that. So let's do a refresher of electromagnetic radiation. So let's call it EM, so electromagnetic radiation. Okay, and let's call it a refresher. I just want to talk about characteristic wavelengths, pretty much. So let's start with electromagnetic waves that have the longest wavelength, and those are radio waves. Radio waves, they have a wavelength of the order of a few kilometers, from a few meters to a few kilometers. So these are used, for example, radio waves are used for radios, okay? I mean, the name says it, but they are emitted by, for example, Jupiter, I think, emits radio waves, okay? So they have a really, really long wavelength, therefore they have a very low energy, pretty much, okay? Now, microwaves, and you're familiar with this from your everyday life, they have a wavelength of the order of magnitude of millimeters, okay? So they are able to excite molecules pretty much like water. What happens when you put your food in the microwave is that the microwave emits these waves that excite the water molecule. Therefore, it gets warm, so your food gets warm. Okay, because 70% of living matter is water, more or less. So, anyway, then we have the IR light. They have a wavelength of a few micrometers. Then we have the visible light. This is the light we are able to see. It has a wavelength of 400 to 700 nanometers. And this is for humans, okay? Because bees can see, I think, from 300 to 900 nanometers, maybe. And other animals have, there is a spectrum in the visible light that various living beings can see, but in general, they are of the order of magnitude of a few hundred nanometers. Then we have the UV waves that have a wavelength of 10 to the negative 10 meters. Okay, we have the X-rays that have a wavelength of 10 to the negative 11 meters. And then we have gamma rays that have a wavelength of the order of magnitude of 10 to the negative, 12. So 10 to the negative 12 meters. Okay, and as we move towards gamma rays, the energy increases. Okay, so gamma rays are the most energetic, and maybe I should also put here that these two are called ionizing. You don't need to know this for this topic, but it's good to know. These are ionizing radiation. Ionizing waves, I'm sorry. And we say that, what do we mean by ionizing? It means that they have enough energy to kick an electron out of an atom. Therefore, they can create free radicals in a living being or break the DNA or catastrophic things like that. Okay. Now, let's go back to stars and talk about that. So this is still giving you a broad overview of this topic. So let's talk about stars. So stars are the major, I'm going to put in parentheses though. So stars are the major source of radiation from space. And some of you will be wondering, so what else is a source of radiation from space? As we mentioned, planets, okay, they emit light because light is reflected on them, but they still emit light and radiation, like radio waves, due to atmospheric phenomena in some planets, for example. And also nebula. These are gases, like hydrogen gases. They span, I'm not an astronomer, I'm a nuclear physicist by training, but I think they span something like, I want to say thousands of kilometers, maybe thousands of actually astronomical units. Yeah, that sounds more right. But anyway, these are huge concentrations of gases in between galaxies or inside galaxies and so on. So actually in between, I think. So, but let's focus on stars. So stars, which are a major source of radiation from space, can be approximately modeled. As blackbody radiators. So what is a blackbody radiator now? So a blackbody radiator is a hypothetical. So this object does not exist in real life, but many objects in real life approximate this hypothetical idealized object. So it's a hypothetical object absorbing all electromagnetic, in the sense of all lambdas, okay, so all wavelengths. So it absorbs all electromagnetic radiation that falls onto it. So why is it black? Because it absorbs all radiation. Okay, but when we look at these objects have the ability, the property of emitting electromagnetic radiation when they are heat up. Okay, so let's write this down. So they are black because of the absence of color. Because, as we said, radiation is absorbed. But only if their temperature is 0 degrees Kelvin, will they appear black? Okay, so if the temperature is risen above 0 degrees Kelvin, they emit electromagnetic, let's write it as EM, okay? So they emit electromagnetic radiation. All right, so let's move on and mention the Stefan-Boltzmann law, which is something you need to know. So the Stefan-Boltzmann law says that if we heat up a metal, say, which is which can be thought of as a black body radiator because it kind of absorbs all electromagnetic radiation. Okay, of course, metals shine, therefore they reflect some electromagnetic radiation, but they cannot be approximated as black body radiators because when we heat them up, they emit certain colors, right? Like if you think of an iron rod, when you start heating it up, it glows red. Then when it heats up a little bit more, it glows yellow, and so on and so forth. So if we heat up a metal at, say, 4100 Kelvin, it glows red, okay? So, which is something I just described. So red color is at a wavelength of 650 nanometers. If we further heat it up, it glows, if we further heat it up to, say, to 5100 Kelvin, it glows yellow. Okay, so this is from everyday experience pretty much. So the yellow color is at the wavelength of 570 nanometers. Now, why do we see the metal glowing as red? Because, okay, when a metal is heated up, it emits all sorts of radiation, but most of it is at the red wavelength if the temperature is, as we said, say 4000 Kelvin. But then when we increase the temperature to 5000 Kelvin, we see yellow, which means that most of the radiation is yellow. So if we go plot the plot of intensity, so if we plot the intensity of radiation, my God, my handwriting is horrible, guys. I'm sorry. Let me erase this. Let's write it again. So intensity of EM radiation. So if we make this plot, this has units of watts, by the way. Okay, so watts is 1 watt is 1 joule per second, right? So if we make this plot against lambda, where lambda is in nanometers, then let's use red for the metal that glows red. So the curve will look like this. So this is 650 nanometers, okay? So this is the metal at T equals to 4100 Kelvin. But if we make the plot of the metal when it glows yellow, it will look like this. Yellow color is here, let's say 570 nanometers, okay? So at a shorter wavelength. So the peak will be here. So it will look something like that, okay? So this is at a temperature of 5,100 Kelvin. Okay. So what do we observe here? That the more we increase the temperature of a black body, the lower the wavelength of the emitted light. But keep in mind that what we said earlier, that most of the color appears yellow in the case of 5,100 Kelvin, because we have most, like if you think about the area under this curve as the number of photons per wavelength, we have the most of the photons in the yellow color. Okay, hope this makes sense, because the metal heated at 5,000 Kelvin emits electromagnetic radiation also at 700 nanometers, 800 nanometers, etc. But that's not the biggest portion of the light. Okay, so let's write this down. That S lambda decreases, the frequency increases because the speed of light is equal to the wavelength times the frequency, and because the energy of the photon is h times the frequency, the energy increases. So as you hit a black body radiator, it will emit more energy. Hence, more radiation is emitted at higher temperatures. So the same graphs we showed for the case of a metal apply to any black body radiator, including stars. So what I'm trying to say is that if we plot I, the intensity in watts, versus lambda in nanometers for stars, then let's say here we will have stars that appear red. Okay, so they have the lowest T. Then we will have intermediate temperature stars that emit yellow. So actually this graph is not good, sorry. So something like this will be an intermediate temperature star, intermediate T, okay? And the hottest stars will emit mostly blue color, okay? So highest temperature, okay? So when I teach this class, I like to show a website that has some simulations about how these things work. So let's go visit that. Okay, so this is a nice website. If I remember, I'm gonna include the link in the description. If not, please remind me in the comments and I will include it. So this is by the University of Colorado, I think. And they have many simulations related to physics. And in this one, they show the spectral power intensity for the radiation emitted by objects. So you can change it here. So this is the sun. This is something with a temperature of, as you can see there, they list the temperature. So 4,250 Kelvin. And I have to zoom out to show the light bulb. Actually zoom in, not out. So, okay. So the light bulb is at 3000 Kelvin, and if you want to see the Earth, you have to come all the way down there. Can we zoom in and see anything? No. How do you do this? Let's see. Okay, here. So you have to zoom out in the intensity, and you see that even the Earth is some sort of a black body radiator, but the intensity of the radiation is really low, as you can see. Okay. So the Earth emits light with the peak at about, okay, this is 48, so something like 10 micrometers. That's microwave level intensity. What else can we do here? Let's see. If we tick that, it shows us the intensity in units of watts per square meter. It also shows us some labels there. Graph values. Okay, so 11.59 micrometers. I said 10 also. Okay, so I was close. Now let's go to Sirius A. So this is the hottest star, I think, one of the hottest stars. So now we have to zoom in and zoom out, sorry. Let's see. Okay, sorry for the clicking sound, it's annoying probably. So for Sirius A, we see there that the peak wavelength is at 0.29 micrometers. That's 290 nanometers. So it's even lower than UV light. Okay, so you see how here they list. Like if I'm bringing my cursor there, this is the visible light. Okay, they include 380 nanometers, which is it's UV pretty much. And all the way here we have 750 nanometers. That's red. So we see that Sirius A is actually really, like if you were really close to the star, you will burn alive because it's UV light. So anyway, you can play with this later. Let's go back to the notes. Okay, now let's move on and talk a little bit about the math of this situation. So the power output. We keep talking about the intensity of radiation, so let's go talk about that. The power output of a black body radiator can be calculated by the Stefan-Boltzmann law. And by the way, I just realized that all the way here I mentioned this as the Stefan-Boltzmann law. So this graph is actually called the Planck graph. The Stefan-Boltzmann law specifically gives you the power output, so it gives you the number of this intensity over here. Okay, so let's go talk about that. So L, the luminosity of a black body, is equal to this constant sigma. Okay, so this is a constant times the area of the body times its temperature to the fourth power. Okay, so this is the surface area and this is the temperature. So sigma is 5.67 times 10 to the minus 8 watts times meters to the minus 2 times kelvins to the minus 4. And the surface area depends on the shape of the object, but if we talk about stars, that's 4 pi r squared, which is the surface area of a sphere, as you know. Surface area surface area of a sphere of radius r, and T is the temperature in Kelvin, okay? And this is in square meters, of course, okay? So this is in square meters for the area, okay? So what are the units of these things? So I think I mentioned this in previous videos, but in case you didn't watch them, if we put square brackets around a unit or a variable, we mean the units of that variable. So we are trying to find the units of this variable, the luminosity. So that's going to be equal to the units of sigma times the units of the area times the units of T to the fourth. So the base units for sigma are watts times meters to the minus 2 times Kelvin to the fourth, to the minus 4, sorry. The units for the area are meters squared. The units for temperature are kelvins to the fourth. So all this gets deleted. So for luminosity, the units are watts. Okay. Now, one more important thing when it comes to the Planck curves that we saw here, and the Stefan-Boltzmann law, is the Wien or Wien, I think, law. So the lambda. Remember when we talked about this peak, by the way? Okay, so this is the peak of this curve, this is the peak of the second curve, and this is the peak of the third curve, okay? So the wavelength of that curve is related to the temperature of the curve via the Wien law, okay? So the lambda, the wavelength at the curve peak, at the curve's peak, sorry for my English, and T of the curve are related via Wien's law, which is given by lambda times T is equal to 2.98, so it's a constant, times 10 to the negative 3 meters times kelvins. Okay, so let's see a very, very brief example. Find lambda for the sun if the radius of the sun is 7 times 10 to the 8 meters and the temperature of the sun is 5,800 kelvins. Okay, so actually find the luminosity, L, I'm sorry. So find the luminosity for the sun. What is the peak lambda? What color is that? Okay. Oops. So let's see. L is given by sigma times A times T to the fourth. So sigma, as we said, is 5.67 times 10 to the negative 8, okay, times the area, which is 4 pi times the radius squared, so 7 times 10 to the 8 squared times 5,800 to the fourth, okay, and the units work out to be watts. So if we do that, we find 3.95 times 10 to the 26 watts. That's a lot of power. Now, let's go find the peak wavelength. So lambda peak times T is 2.98 times 10 to the negative 3 meters Kelvin. So lambda peak is 514 nanometers. That's green. Now, why is the sun white? Because, can you think? Okay, if you thought for a moment, the answer is because you have a mixture of lots of colors near green that mix up and give you that nice white or white yellow color. Okay. Let's stop the video here, and we are going to continue with the rest of the material in other videos, because this is a lot of material for you. So I'm going to break this last topic into several videos. I hope that this new iPad gives you better quality. I also bought a microphone and stuff like that. I'm going to start testing new ideas, and I'm going to give this channel an upgrade pretty much. I'm going to try to teach quantum mechanics and other college level classes. We'll see.